Hello students, let's begin with a thought. Why do ceiling fans or transformers resist sudden changes in current? The secret lies in inductance. Imagine we connect a pure inductor to an alternating voltage source. The voltage is given by V of t equals Vm sine omega t. By Kirchhoff's loop rule, this must equal L times di by dt, where L is the inductance. So, the inductor resists the change of current by generating a self-induced EMF. This is why inductors are often called the inertia of electricity. Just like mass resists acceleration, inductance resists current change. Now let's see what happens when we connect an inductor to an AC source. We start from the differential equation L di by dt equals Vm sine omega t. This simply comes from applying Kirchhoff's law to the circuit. The voltage across the inductor must equal L times the rate of change of current. When we integrate this equation, we get I of t equals negative Vm divided by omega L multiplied by cosine omega t. That's one way to write the current. But we can also express it more elegantly. Since negative cosine omega t is the same as sine omega t minus 90 degrees, the equation becomes I of t equals Im sine omega t minus 90 degrees. Here, the current amplitude Im is given by Vm divided by omega L. So what does this mean physically? The current through a pure inductor always lags the applied voltage by exactly 90 degrees. In other words, the current wave is a quarter cycle behind the voltage wave. Quick insight, that's why inductors are called lagging elements in AC circuits. They delay the current compared to the voltage, a fact that becomes very important in power systems and electronics. Students, now that we know how current behaves in a pure inductor, let's define a very important concept, inductive reactance. We write it as XL equals omega L. Here, omega is the angular frequency of the AC source and L is the inductance of the coil. This reactance XL plays the same role in AC circuits that resistance plays in DC circuits. It limits how much current can flow. From this, the amplitude of current comes out as Im equals Vm divided by XL. So the larger the reactance, the smaller the current for a given voltage. And what are the units of reactance? The same as resistance, ohms. That's why it behaves like a frequency-dependent resistance. Here's a quick insight. If you increase the inductance or the frequency, the reactance XL becomes higher and the current becomes smaller. That's why inductors naturally oppose rapid changes in current. They resist fast fluctuations more strongly. Students, now let's look closely at what makes inductors so unique, the current lag. In a pure inductor, the voltage Phasor leads the current Phasor by 90 degrees, or in other words, by a quarter of a cycle. This is the hallmark behavior of inductors. If you observe the time graphs, the voltage curve V of t rises and falls first, while the current curve I of t follows behind with a quarter cycle delay. That means at any instant, the current peaks always occur later than the voltage peaks. The Phasor diagram makes this even clearer. The voltage Phasor V is ahead, and the current Phasor I trails behind by exactly 90 degrees. This visual proof shows how inductors oppose changes in current. So the quick insight here is simple but powerful. In pure inductors, the current always lags the voltage by 90 degrees. This lag is not just theory, it's why inductors are used in tuning circuits, filters, and power systems where controlling phase is crucial. Alright students, now let's tackle an interesting question. Does a pure inductor actually consume power? To answer this, let's calculate the instantaneous power. Power is voltage multiplied by current. Substituting, we get P of t equals Vm sine omega t multiplied by Im sine omega t minus 90 degrees. When we simplify, it reduces to P of t equals negative 1 by 2 multiplied by Vm multiplied by Im multiplied by sine 2 omega t. Now here's the key observation. This expression is sometimes positive, sometimes negative. That means in one part of the cycle, the inductor is absorbing energy, while in the other part, it is giving that energy back to the source. If we average this power over a complete cycle, the result comes out to be 0. So the inductor does not consume any net power at all. The physical meaning is simple. An ideal inductor stores energy in its magnetic field and then releases it back without dissipating it as heat. Quick insight: this is why ideal inductors are lossless elements. They don't waste energy, they only borrow it temporarily and return it. Alright students, let's put our understanding of inductive reactance into practice with a real example. Suppose we have an inductor of 25 millihenry connected to a supply of 220 volts at a frequency of 50 Hz. We want to calculate its reactance and the RMS current flowing through it. Step 1. Reactance. The formula is XL equals 2 PIFL, substituting the values, 2 pi multiplied by 50 multiplied by 25 into 10 to the power minus 3. That comes out to approximately 7.85 ohms. Step 2. RMS current. Now current I equals V divided by XL, so 220 divided by 7.85, which gives nearly 28 amperes. Final result, the inductive reactance is 7.85 ohms and the RMS current flowing is about 28 amperes. Quick insight: this large current shows why inductors with small reactance at low frequency can draw significant current, and this is exactly why phasor diagrams are so useful. They let us visualize how reactance controls current flow in AC circuits. So let's wrap up. In a pure inductor, the current lags the voltage by 90 degrees. The opposition to current is not resistance, but inductive reactance. XL equals omega L. An inductor stores and releases energy in its magnetic field, with zero net power loss over a cycle. And finally, frequency plays a crucial role. The higher the frequency, the stronger the inductor's opposition to current. I hope this session helped you see why inductors are indispensable in filters, transformers, and AC machines. In our next session, we'll explore what happens when AC is applied to a capacitor, and you'll see an exactly opposite phase relationship. Stay tuned.